Hello, good morning, good evening, good afternoon, everybody, wherever it might be. And most importantly, bom dia, Brazil. So we are very happy to host a seminar from Florianopolis. However, our speaker is just across the pond in Trieste, Italy. And he will tell us everything and more about the moduli of representations of the Cuntz algebra obtained via Von Jones technology. Arnaud, it's all yours. Take it away.
All right. Well, thank you very much, Piotr, for the invitation, and Francesco also to give a talk at the seminar. Also, thank you for the organizer to maintaining this great online seminar. So what I'm going to discuss today is about a work that initiated quite some time ago, I'll say in 2017-18. I joined a project that Von Jones initiated and we work on it. And later on, I continue to develop like a technology for it with one of my PhD students, Dilshan Vijayzena. And this work is really about constructing in an explicit and efficient way representation originally for the Richard Thompson's groups. And actually we figure out that it was maybe even more natural to do it for the Cuntz algebra. Okay. And we'll see that I'll develop like powerful tool for classifying them. Okay, so that will be really what I want to do today. Okay, but yeah, let's start. So I'll be doing like a mix of slides and maybe writing a little bit on my surface. We'll see how it goes. So first thing, what are the main objects we're going to look at? Well, we're going to look at, I should say, the Richard Thompson's group, not the sporadic finite group given by the other Thompson, but the one of Richard. So that was in.
Yeah, I really appreciated it in your abstract that you made it clear, because there are two Thompsons who are super famous for their groups. So
yeah, really... that's right. So let's say that when there is a last name that is, you know, there's many Jones, for example. So I said Von Jones. And for Thompson, there's two very famous group theorists, both of them, called Thompson. So that's why I always insist to put Richard. Yeah, I didn't put him for Cuntz because we know there's several Cuntz, I'm sure, but there's one.
Cuntz exists and is unique.
Yeah, there's one is very famous. Yeah, more famous than the other. Okay, so I'm going to look at three different groups that were discovered in the 60s by Richard Thompson, I believe, when he was doing his PhD actually in Berkeley in logic with Ralph Mackenzie, I believe. And he never published it, but it just opened the whole field of itself, actually, these groups. Yeah. So what kind of beasts they are? Well, they are countable discrete groups. Okay, just to fix the idea, they are infinite countable. There are three of them. So, and the traditional ones that today we write them F, T, and V. Okay. And they all act on the Cantor space. So by that, I mean the infinite binary strings. Okay. And how do they act? Well, they locally change a finite prefix. And they act by homeomorphism. It means that they don't change. There's only a finite number of prefixes that will define an element of F, of T, or of V. Okay. So what's the difference between the three? Well, the first one acts in an order-preserving way, while T will be, if you want, it acts in a cyclic order-preserving way. Okay, so it's a bit like F plus the rotation. And V doesn't care about the order, right? So if you take the projection of the Cantor space on 0, 1, on the real unit interval, F will be acting by homeomorphism on 0, 1, while T will be acting more on the circle. So you will need to identify 0 and 1 to allow translation, or if you want rotation. And V will be only continuous on one side. Okay. So you will have like element of V will have finitely many discontinuity points, possibly. All right, so they are quite, when they arrived, they gave properties that were never witnessed before. So people are very intrigued by them. I should say that all of them are, well, they are infinite, you can prove it, and they have a finite presentation. Okay. And very unusual properties. So what kind of unusual properties do they have? Well, F, for example, he will have no finite dimensional classifying space. Okay, so we'll have infinite geometric dimension. And moreover, it's torsion-free. And it's finitely presented. So that was the first example of this kind, actually. Okay, that was seen in the 80s. But maybe even more striking, and to me, it's always a great surprise to see that, is that the group T and V, they are simple. Okay. But actually, they were the first infinite simple group with finite presentation that were seen in nature, that were discovered in mathematics. So we know so much about simple finite groups. You imagine that we know also a lot about infinite simple group, but actually not at all. We had to wait the 60s to have like the first examples that are finitely presented. Okay. And you could see that nowadays, I would say almost every construction of infinite finitely presented simple groups, they derive from the construction of the Thomson's group. Okay. To me, maybe the only exception that are a bit further away from that are the construction of Bourget and Moses with automorphism of trees, and the one of Capras and now I can't remember the co-author, Remy, I believe, yeah. Okay, that are more like with Kac-Moody technology. Okay, and since I'm going to talk about, well, I should say one thing. Since the beginning, actually, it's been, well, it was quickly observed that F does not contain a copy of the free group, okay, of the non-abelian free group. And people thought, well, maybe it will give like a new example for the von Neumann-Day problem, you know, that was like this problem that asked how close it is to be non-amenable and to contain a copy of the free group. But then people try to prove or disprove that F was amenable. Okay, and this is still open today, and that's probably the most famous conjecture concerning the Richard Thomson's group. It's hard to say how much interesting would be to answer this question, but what is very interesting is all the technology that's been built on trying to solve this question. Okay. And I think this question of amenability got quite famous thanks to the work of, I would say, Matt Breen, Joe Higan, Kenneth Brown in the 80s, a bit before. Yeah.
And correct me if I'm wrong, this is still not set, right?
It's not set. Actually, we still don't know if it is also weakly amenable in the sense of Cowling and Hagerup. And something even more crazy, we still don't know if it is exact. We still don't know if there is a single action.
But wait, it satisfies Baum-Cohn, right?
It satisfies Baum-Cohn because they all have the Hagerup property.
Okay.
Yeah,
and
but
logical
this
hyperlinear we don't know either, right?
we don't know if they're hyperlinear. That's right. Yeah.
Adam, you had a question.
It's really amazing. Yeah.
Yes, I have a quick question. Could you repeat? So this conjecture is about T or V also?
Oh yeah. Thank you for asking. Yeah. The conjecture about amenability is for F.
For F.
If it is amenable or not.
Yeah. And for
it
which
is actually
the answer is no?
The answer is unknown. We don't know if F is amenable or not.
No, but you said that for one of these groups, the answer is actually known.
Yeah. For T and V, we know they contain a copy of the free group with two generators.
Okay, thank you.
Yeah, and we know that all of them have the Hagerup property. So you know the Hagerup is kind of a weakening of being amenable in an analytical asymptotical sense, and so we know that at least they have that. But in fact, it was conjectured for a while, like people didn't know if they had the cache-down property T or not. And it was only answered in 2003 by Reznikov. And then also with the beautiful work of Gis, Sergiescu, and Navas, that they don't have property T. And then Farley gave like this amazing proof, 2003 also, or maybe Reznikov was a few years before. And he shows that V has a regular property, so all of them has a regular property. It's like a very quick proof, actually. Okay, so that's a bit what we know about analytical properties, so not much. The only thing we know is that it's inner amenable. And that was proved by Paul Jolissin in 97, I believe. Okay, but today I'm going to talk a bit about representation. And for me, actually, a representation of a group is always unitary. Okay, so I forgot to write it everywhere, but I only look at unitary one. And one fact that is good to know is that if you take an irreducible representation of F, it's either of dimension 1, in fact, it's factorized by the abelianization, or it's infinite dimensional. Okay. It's just to say that it's just a fact to say it's not so easy to build representation in general for this group and to check if they are irreducible. It's always a hard question for infinite groups. Okay, so that's about F. Would be one of the actors of this talk. A second will be, well, I should say the Cuntz-Dixmier algebra. I'm going to call it the Cuntz algebra, but I should remind everyone that Dixmier discovered this algebra in 1964. Okay. But he couldn't prove everything he would like to prove. Like he knew it was important, but he was not sure if there were like a quotient of it or not. And then Cuntz in 1977 has this beautiful paper when he could prove much more. Yeah. It's such a nice paper because he starts algebraically, basically doing what you would like to do for the Leavitt algebra, and then he does like the analytical part after. And so this sister algebra is a universal one generated by this relation. So what does that mean? It means that you have two isometries, S0 and S1, and their range is orthogonal, and they generate the whole space, okay, for any representation of it. Okay.
Sorry, Arnaud, correct me if I'm wrong, but I believe that Leavitt discovered these algebras on the purely algebraic level to study this lack of dimension property for free modules already in 1962, right?
Yeah, or even actually, I think in 1954, actually.
Wow, well, that's even better, yes.
We can give yeah, it was different context. I don't know how much they talk with each other, how much Dixmier knew about it. But yeah, it was before. Is it 54 or is it 60s also?
I had an impression that it was 62, but it's.
You may be right, because at some point I remember that all these things were the same decades, because Thomson 65, Dixmier 64. Yeah, it could be that.
Because
yeah,
you know,
right.
I had to one time dig in why Leavitt path algebras are Leavitt path algebras. And then I went back to the original work of Leavitt and see what Leavitt algebras are. And these are Leavitt algebras with one index 1. And then I'm pretty certain that it was 1962.
Okay. Yeah, by the way, everything I'm going to talk about applied to the Leavitt algebra. So maybe I say that at some point.
Yeah, you mean Leavitt path algebra. Yes.
And even to the Leavitt path. Yeah. Such like the Leavitt path being the corresponding Kuntz-Krieger algebra. Well, exactly. Here the Kuntz is the Leavitt. Yeah, exactly. All right, so this Kuntz algebra was the first example of something that was separable, purely infinite, meaning that it's kind of like a type 3 factor in fundamental algebra land, and simple. Okay. So it means there is no quotient. So it's one brick. It's always hard to prove that something is simple for groups. For sister algebra, there are other techniques. But here it was very subtle to prove it. And if I don't think I need to sell the Kuntz algebra to the seminar, how important it is and how much it's been central. So let me just talk about the representation. Well, if you take a look at the presentation of O, you can see that if you take a representation of it, it's going to be infinite dimensional, no matter what.
Mhm.
Why? Because basically you get isometry between your space and a sub-piece of it, right? So you
Yes.
basically manage to say your space is the same as this space plus this space. Yeah.
That's exactly what Levick was interested in.
Yeah, that's right. Yeah, to get like A isomorphic A2, something like that. Yeah. And also, I should say that in this talk, as you can see, everything is binary. I'm looking at the Cantor space of binary string. I'm looking at the second Cuntz algebra, but actually, everything that I'm saying, you could take it n-ary. So to take like the nth Cuntz algebra, the nth Higman-Thompson's group, etc., acting on the Cantor space of n letters.
Sorry, just a quick
Okay.
question. So,
Yeah.
since I don't understand this fact that all representation are infinite dimensional, would easily follow if we already know that this algebra is simple, yes? And infinite dimensional itself as an algebra.
Oh, because the Cuntz algebra is infinite dimensional, and then you're having your morphism. It has to be injective, so you get like an injection. Yeah, yeah, you're right. Yeah, yeah.
Yeah, but so maybe probably. So correct me if I'm wrong. That this fact that all representations are infinite dimensional was proven earlier, and the fact that this algebra is simple was more difficult.
Oh no, showing it's easy to prove the representation are all infinite dimensional, but it's difficult to prove that the Cuntz algebra is simple.
I see.
Like
okay.
I would say proving that they're all infinite dimensional is more an exercise, but proving that it's simple, like Dixmay was stuck on it.
Mm-hmm. Okay,
So
okay. That makes sense.
That's a difficult thing. Yeah.
Mm-hmm.
And really he proved it like in what you would do in a finite algebraic structure. You take one element and you say if you hit it from the left and right, you generate everything. That's what did Cuntz. So, yeah, very explicit and yeah, in the hard way in some sense. And one last thing, and this is really to sell all my theorems that I'm going to take that, is that this is a non-type 1 sister algebra. So this means that there are some representations that will generate type 2 and type 3 von Neumann algebras. And why is it interesting from a representation theoretical point of view? Well, it comes from a theorem of Glim from 61 in the Annals, actually. And what do say Glim? Well, I was giving a talk last week in Rome about that, and I paraphrase a bit the theorem of Glim. I was saying that if your sister algebra is type 1, you can go home and go to sleep if you try to understand its spectrum. Basically, Glim theorem gives you a bunch of equivalents that tell you that if you look at the irreducible representation of O and you mod out by unitary equivalence, well, this space, there is like a canonical topology you can put on it, I mean, a classical topology, I should say. And it will give you a space that is very badly behaved. Okay, it's not going to be Hausdorff, it's going to be like nothing will work. Yeah. And in general, if you talk with someone about the Cuntz algebra and you tell him that you want to look at the irreducible representation, you want to classify them, he will tell you, well, good luck because it's non-type 1. And in some sense, you know, it's true. But here we're going to get like a very different point of view that will give us a parametrization. Okay. Exactly like often it happens in algebraic geometry, you have like a bunch of objects, you want to classify them, and you get like something, it can be functorial or ad hoc, but you get like a very nice bijection of your set of irreducible class with something that is geometric, like a manifold or algebraic variety. And that's really what we get here. We'll get some differential manifold. Okay. All right. So punchline here, difficult, mysterious object, FTV and O. It's very difficult to construct representation of them. Why I'm talking about both of them? Well, there is a very tight connection between the Thompson's group and the Cuntz sister algebra. And that was something discovered in 2014 independently by Birget and Nekrashevich. And here I always put Birget first because his name starts with a B, so there is no like I actually enjoy both of the articles. So I really like them. They were the same year, as you can see. And they show that actually there's a very natural map, a very, natural in the English sense map that goes from V actually to the unitary group on the Cuntz algebra. Okay. And so to me,
I think
when
there are some questions. Guys,
Yeah.
ask questions while waiting for me.
My question is, does it generate the algebra, this image of the group V?
Well, if it is, if you want, I'm not replaying exactly, but it's going to be the normalizer of the Cartan subalgebra, the usual Cartan subalgebra given by the Cartan space. So if you take the normalizer of the Cartan subalgebra and you mod out by the unitary of the Cartan, it's exactly the image of V. Okay. So it means that it's all the stuff that make move the Cartan subalgebra. Yeah. So it's very
Oh
neat.
my God.
Nekrashevich explains that in great details actually in his article. Yeah. And everything is very explicit. It's really nice. Yeah.
Just a quick question to ensure myself whether I understood you correctly. This bad behavior of the space of representation is for non-type 1 algebras, yes?
Oh no. Is that me? Oh,
Yeah, you got frozen for a while.
oh, okay. Yeah, you got frozen. Me also. I hope yeah, it's working correctly. My computer seems to not be too hot. But go ahead, Adam. I didn't catch your question.
Yeah. Okay, so just to ensure myself whether I understood you correctly, so this bad behavior of the space of representation is for representations is for non-type 1, yes?
Exactly, yeah.
Okay.
If you are type 1, everything works better. And in fact, you'll get like a nice bijection between isomorphism classes of irreducible reps with primitive ideals.
Primitive ideas, yeah.
So you get that. And actually, type 1 is equivalent to not having that. Yeah. Yeah. Okay. Yep. So I think now what is the plan is that I connect a bit this object and I. Question.
I have a question. Yes.
Yeah. Go ahead.
It's about this embedding of V in the Cuntz algebra. You said something about the action of this V. So is the action on the maximal abelian subalgebra by
conjugation,
like a normalizer?
Exactly.
Yeah,
it is sent to the normalizer of the Cartan subalgebra.
Okay, thank you.
And then when you mod out by the unitary of the Cartan, it's exactly it's isomorphic to V actually. Yeah.
Okay, thank you.
So it's very neat. Yeah. Well, thank you for that question. I think I was planning to do some forest now. Yep. So this will be for after. I'm just gonna write down a little bit on my tablet. We'll see how it works. Huh? I hope so. Okay, so you should be able to see a blank piece of paper. Yeah, with a category of binary forest. So let's see if I can do that.
It's not completely blank. We see some scribblings.
Okay, there's some scribbling. Very good. All right, so I'll try to talk about the category of binary forest. And the plan is to give a structure of categories. And actually, I'm going to put two products on it. Then I will explain why I'm talking about that, because the Thomson's group will pop out of it, the F1. Then we get the larger Thomson's group.
Sorry, could you change the color?
Oh, yeah. Let's see. Maybe I put in black so it's
something darker.
Okay. Yeah, I'll put black. And after I'm going to say how functors.
Oh, much better.
Okay, excellent. Yeah. Functors of F gives unitary reps of F. in fact, of the three. And then after, I will explain why it gives me actually also a representation of the Cuntz algebra. Right. And so far, I only did one slide, so we'll see if I do 10 slides in 1 hour and a half. I'm a bit slow, but yeah, we'll see.
But no,
Okay,
the
so-
absolute record, you will not beat George Eliot. I remember.
I don't know why
when-
I was about to say.
Yeah,
maybe George Eliot.
yeah. Once he gave a talk in Warsaw, and the talk, I think, lasted at least 1 hour, maybe 90 minutes. And he wrote just one blackboard, not more.
Okay.
I took a picture of a blackboard and I had full record of his talk.
Oh, well, we'll see.
Okay,
Maybe I'll
anyway.
do 2 blackboards today. Yeah. Okay, so what is F? So for me, F, well, it's a category, but I kind of like to think of it as a set, okay?
Okay.
As a set with a partially defined operation. I
Okay.
hope it's fine with everyone. But yeah, so the elements that are in it, well, it's kind of explained by the name. They are forests, okay? And here I say that there are 2 roots, and here I say there are 5 leaves. So if I want to think of a category, I would say it's a morphism from 5 to 2. Or I could just say that I have a forest like that. And then I can define two things. So the composition, which is what? Which is horizontal concatenation.
No,
Horizontal or vertical?
horizontal.
Oh, no, you're right. No, I'm making a mistake
Vertical.
already. It's vertical, of course. Yeah. So I'm stacking.
Yes.
And the tensor product, so it's a monoidal product if you want. Monoidal. Actually, I enjoy category, just like here, I think it's better to see it as a set, but no. And here it's horizontal.
Yes.
Okay, so if I take this guy and I tensor with this, well, it's kind of, I just remove the symbol of the tensor product, right? But then if I want to take a composition, so I take this guy and I'm going to compose on the top. So I'm going to put maybe something not too big. So this will be equal to where I start below as I started, and I'm added some stuff. So yeah, I don't really add much. Add that.
Too much.
Yeah. Okay. Okay. All right. So I get that. And you can see that you're allowed to change a little bit your diagram. Like if I add a little bit like that, if I add this, that's the same diagram. So it's, as usual. If not, I'm not able to draw. Okay, so that's my algebraic structure. It's a category. And now I can look at action of it. So let's look at, well, maybe I should look at Thompson's group F, sorry. So let's look at Thompson's group F, what I want to say. Yeah, let's say it's a nice category with a calculus of fraction. So the keyword is really calculus of fraction. What does that mean? Well, here I will say that because the category is cancellative, okay, so I can simplify from the left and right with respect to the composition. And moreover, there are common right multiples. So this last axiom, what does that mean? Well, you take 2 forests, let's say F1, F2, And let's say that here they have the same number of roots. So let's say n roots. And here there is also n roots. Okay. So it's the same. Well, if you have that, you can find two guys on top of it, H1, H2, some forest. Whoop. Ah, it's not big enough. Well, such that, well, if I stack them on top of it like that, well, they get equal. Okay. So we say they have common right multiple, because if you take two guys that start with the same number of roots, you can always grow them such that they become equal. Right. And this gives you a calculus of fraction. So that's something that was, I mean, in the abelian case, that was understood a very long time ago. It's like getting from ring to field. But if you are not abelian, that was figured out by Orr in the 30s, how to do that. And for the categorical point of view, it was very well clarified in the 16s by Gabriel and this man. Okay. Okay, so what does that give me is that I can formally invert, I guess. I can formally invert forests. And then I get a groupoid. Okay. And so any element of this groupoid, so I get like a so-called, usually we call it, it's called a fraction groupoid. Okay. And so element of it are of the form. So graphically, it's very easy to see what they look like. Well, you will have one forest here, and you will have one upside down. So it could be a tree, for example, like that. Okay. So all of them, if I call that F and I call that H, I will call this guy F composed with H minus 1. So I formally invert forest, and now I can just draw them upside down. And this axiom tells you that everything works well, and also tell you that if you have something like that and you have another one, F like that, well, this will be equal to a certain F hat. So what I mean is that if you take a signed path, it will always be at most of length 2. Okay. It will be everything on the left with positive indices and to the right with a minus power minus 1. Okay, so that's very nice and very easy to, it's a nice algebraic structure, let's say. Now, why do I talk about that? Well, because if I take the isotropy group of frac F at the object 1, in fact, at any object, I obtain Thompson's group F. By that, I mean it's isomorphic to Thompson's group F. Okay. So to me, it means that F, I can kind of see it as a bunch of T composed with N minus 1, where TS are trees with same number of roots. Okay. And this group lives inside the fraction groupoid. So an element
by the object 1, you mean the monoidal unit, or what?
Well, then by 1, I mean there is only one root.
One root, okay.
So then it means there are trees. And you're right, I was saying I don't want to use categorical term, and now I talk about objects. I'm a bit... So an element of F will be something, for instance, like this one. Yep. Okay, so I have one tree here. and I have another tree here upside down. Okay. And this, you can see it. I mean, this description with trees without talking about categories was done by Vaughan in the 80s. Okay. You can see it was published in 87. And in fact, I was talking with Murray in Sydney, my elder, and he was telling me that when you read the notes of Thomson, it is very clear that he already understood that you could use trees to describe elements of the Thomson's group. Okay. Well, Thomson didn't publish anything, but well, can believe he had that. And Brown wrote it very well because Brown always writes extremely well. Yeah. Okay. All right. So this is, yeah, we get like an instance of one of the objects we would like to see. And so let's see what I was planning to do. Yeah, we got Thomson's group F. How we get the larger one? Well, the larger one. Well, you add permutation of leaves. So what do I mean by that? Well, you could just take back what you had before, my two elements, but now in between, I can put a permutation, let's say something like that. Okay. And this will give you, you could redefine actually the whole category where now you have forest with permutation that I can express with diagram of this type, and everything works. Okay. And so if you take cyclic permutation only, you get Thomson's group T. And if you take all permutation, you get Thomson's group V. And actually, could be even more courageous. You could take braids. Well, you get something often written BV that is sometimes called the braided Thomson's group. It's also a very interesting group that was defined independently the same year actually by Brin and ARNAUD. Now I blank on the year, I think it's 2004, but I'm not sure. Maybe. Okay. All right. Cool. So we get that. We get some nice groups. And now I think I probably want to promote. I want to look at representation a little bit. Yeah. Okay. So probably now I'd like to talk about Jones technology. I may come back to the slide and quickly work on this. Yeah, I want to do that. Okay. All right, so I'd like to talk a little bit about Jones technology, and we'll come back to the trees to see how it's going to work for a specific key example. Okay, it will be very key for us. So I would say that at the beginning of 2000s, I remember hearing Vaughan talking about that in 2011, actually in Maui at a conference, how to approximate conformal field theory using subfactors and string diagrams. But the first paper arrived on arXiv in 2014, published in 2016. What he got is that he defined a process, a very general process that is functorial and very explicit, that lifts actions of a category. So for me, action of a category is just a functor. Okay. Into an action of the fraction group width. Okay, so you take a category that is nice, that has a calculus of fraction, just like the category of forest. Well, if you take just an action of this category of forest, which is a very basic object mathematically, you get an action of something much more rich, the fraction groupoid. And then you restrict this action of the fraction groupoid to isotropy subgroup. And for us, it will be Thompson's group F, T, or V. And then boom, just by taking action of a very simple object, the category of forest, you get action of very difficult, complex object in mathematics that are the Thompson's group. Okay. And
sorry, the quick question. This action is on what? What is X?
It could be anything, basically. The X that you will get, the X that is here, it will really depends on this category, this target category, and the kind of functor you take. Okay. And so just to give a few examples, let's take now, I fix my category to be the category of binary forest, the one we just saw. And I take a functor that goes in the category of groups. Okay. Well, it will give me an action of Thompson's group F on this guy will be a group. Okay. And by doing that, you can do, in fact, if you want, you can take like a semi-direct product and you can actually extend it to the larger Thompson's group like V. And by doing that, actually, I was able to find new example of infinite discrete group with a Hagorup property that's never been discovered before. Because all the theorems that were known in that direction for this kind of groups, they were done geometrically using Gromov itiminability. With this kind of technology, you have access to many representations. So actually, it can be very flexible. It can become technical, but at least it's very flexible. It's a different angle of attack. So actually, looking at this kind of functor can be very fruitful. Okay. Well, now, if we change, let's take the category of vector spaces. Okay. Well, you get a linear representation. Right. So you see, depending on what kind of target category you have, your action will kind of get some of this structure. And for today, because we want something with a bit of analysis, I will take, favorite category for quantum mechanics. I'm going to take the category of Hilbert space, but I'll do a thing a bit unusual, is that I'm just going to take the linear isometries for morphism. So I only allow to have linear isometries. Well, if I take this...
If I could ask you...
Yeah, go ahead.
There's a quick question, since I'm a little bit confused. In the three examples, in the first, you have your phi goes from F to the category of groups, and you obtain an action on a group. But in the second case, in fact, representation is not morphism into vector space, but in fact, it is a morphism in general linear group of this vector space. So is it right as it is written, or maybe...
it's a linear representation of F. So for me, it's a map from F to a GL of something. GL of V for a vector space V.
Okay. It's fine. Action of group is also goes into automorphism of this group. Okay, it's fine. Sorry for bothering.
Okay, it's fine like that. Okay. Yeah, maybe the term linear representation is a bit, it's just like a usual algebraic representation.
No, it's okay. It's okay.
Okay.
Just I was confused. Sorry.
And the last one, which is really neat, especially for looking at analytical properties of Thompson group F, is that if you take a functor in the category of Hilbert space, you restrict to isometry, there you get a unitary representation of Thompson's group F. So that's pretty nice. So really you get like a map from the unitary of a certain Hilbert space. Okay. And so from there, you can take, if you want matrix coefficients, you can get positive definite function on your group. You can get cross coefficient. You can get completely bounded maps on your group. So many things, yeah, Hertzschild multiplier, etc.
Ask something. Is it too much to hope that every representation may arise this way?
Well, it's a great question. Let's say that I will look at one specific class today. And here we can see that not all representation arise this way for a specific class of functors. Okay. But for general functor, actually, I don't know. Yeah, this I don't know. But the class I will show, they're kind of special because actually all their matrix coefficient never tend to 0 at infinity. Yeah. So actually they look a lot like the Koopman representation, and they look a lot to, we'll see that we'll recover many quasi-regular representation for parabolic subgroups. Yeah. So they kind of behave the same way. Yeah. All right. Okay, so maybe I'm going to look at a very specific class of functor, and I think that should work with my slide. Do I want to put this slide before? Oh, it doesn't matter. Maybe I'll start writing. Okay. Oop, maybe I zoom a bit to have a lot of space. So I put a little bit a specific class of functors. Okay, so what I'm going to take is that I'm going to take Hilbert. So it's going to be the category of, I didn't say it, but complex Hilbert spaces. And morphisms are what? Well, they are linear isometries. And moreover, I'm going to put a monoidal product. And it's going to be actually the direct sum. So it's a bit weird to do that. You will say, oh, you don't take like the usual tensor product. No, I don't. I'm doing a different construction. And it makes sense to sell the usual tensor product. That's actually the first kind of representation I looked into. And it can be very, very powerful. Here it's going to be a bit different. For those who like free probability, you could do Voiculescu free product for pointed Hilbert spaces. Nobody did it, but there is certainly interesting thing to do there. All right, so I'm going to do that. So, and now I'm going to look at some phi. Then I'm going to go to F to this category that I just described. I'm going to say they are monoidal. And what does that mean, really? Well, I'll tell you now what does it mean to be monoidal and to go here. Well, it means that if now I look at it as a category, for any natural number, I should have a Hilbert space, Hn. And if I have a forest, let's say this one, okay? So, well, let's say this one. So here you see there are 3 roots, here there are 6. So this should send to a map that goes from H3 to H6, and it is isometric. Okay. Now I just said that it was monoidal. So this guy, I'm going to call it phi of my forest, right? Can write it like that.
Is this construction somehow related to topological quantum field theory? Does it look in some sense?
Well, it's it kind of looked like it because, but it's only analogous to, I would not say it's related. Yeah, it will be a bit a strong word, but I will say it's analogous to it. Yeah, because it's true that you get like, you know, Bordism, etc. And yeah, functors.
It's a one-dimensional field theory.
Yeah, because you mean for the trees, yeah. with different limitation, let's say. Yeah. But yeah, you could get something very similar. So you get that. And here, because it's monoidal, this should be the identity plus phi of this guy plus phi of this guy. And because it's a monoidal, this guy should be n times the direct sum of H1. Okay. So in fact, such functors are determined, determined by a single Hilbert space H, which is our H1, and a single isometry. By isometry, I mean linear geometry all the time. And this isometry, must have space, that's true, is going to go from H to H plus H. Okay. And that's the phi of that, in fact. So all we need to know is that. So that's why I'm saying like it's very easy to build such a thing. Okay. So now what does that mean to be an isometry? Isometry from H to H plus H. Well, you could just take the legs. Okay, so you will get like two operators like that. Now they become operators from H to H. And you want the isometry condition, where the isometry condition is that is the identity of the Hilbert space. Oh, okay, that's nice. So what I will just say now, I'm just saying that the functor that are, let's say, monoidal from my category F to Hilbert in his bijective one-to-one correspondence with representation of the C-star algebra. I'm going to call it P, generated by two operators and satisfying this relation. I take the universal one, right? Okay. Well, this C-star algebra is a so-called Pythagorean. Oh, the red is not the best. Pythagorean algebra, okay, that we got in this paper with Jones in 19. Okay. And so now I just need to apply this so-called Jones technology to get an action of F. Okay. So how do I do that? Okay. So I fix one map. Okay. Given by A plus B, with A plus B isometric. I'm going to construct a operation of F. To do that, I need to do an inductive limit. I'm going to do an inductive limit of Hilbert spaces. What do I take? Well, I'm going to take T, a tree. Let's say T is equal to something like that. I'm going to define H of this tree. And what it is? Well, it's going to be this tree, but with any decoration. Okay. So really by this, I mean, this is just H to the power of the leaf of my tree. Okay. I'm just decorating the leaf of my tree with element of H. And now I'm just gonna embed all these guys into each other. So I'm gonna take this guy, and I'm gonna embed, but maybe I want to grow this tree. So maybe I will add a caret right here. Okay. So how does it work? Well, I'm gonna take an element. I want to make it grow. Well, here I'm going to keep my decoration intact. And here, where I have a caret, the only thing I can do is to apply A and B. Whoop. So I apply A and B to my vector xi2. And that gives me an isometry from H to this little tree to H of this bigger tree. And now I can just take the inductive limit. Okay, great. Now I can just take, maybe I call it H infinity over 3 of this HT. Okay. And because all my maps are isometric, I keep the Hilbert space structure, I keep my inner product. So at the end of the day, if I take the inductive limit of vector spaces, I have an inner product, and I just need to complete, I have a Hilbert space. Okay. And I'm going to act on that. So how do I act with my Thompson's group F? So now I'm going to take G in F. And G is going to be, for example, this guy. Okay. So it's going to be one tree composed with another tree upside down. Okay. And now I'm going to take an element of H, the H infinity. Okay. Well, up, I may just take eta in a dense subspace. So I'm going to take eta, let's say, in H of a certain T, because they all sit inside it, right? Okay. So I said eta is actually this tree with some decoration. So how do I act on that? Well, let's see. So in terms of diagram, it's going to be very simple. And then this guy, I see it as this tree decorated. Okay. Well, what do I want is that I want that this tree and this tree are equal. This is not true, so I'm just going to grow them. So I just need to add a caret right here. And I rectify on the left. Okay. So now I'm going to say that these two, they cancel out. And so this gives me, I keep my decoration on top, but I change the tree below. I'm going to take now this guy. Okay. And that's the action. And that's a unitary representation. So now, what do I say? I just say that take AB in BH, satisfying this thing. Oop. Where I give you a unitary representation of F. Okay.
Sorry, is it independent of the way you grow the tree? I mean, because
no, because it's really sorry, for the action, yeah, everything is independent of the choice of your vector and the way you grow, the choice also of the tree pair that represent your group, Thompson's group elements. Everything is independent of that. The only thing that matters is that when you need to grow, you need to apply A and B. So here, the unitary representation of F, I should write it pi of AB. We go to the unitary of a Hilbert space that depends on AB. Okay. The only thing that matters is this choice of operators A and B at the beginning. Yeah. And in fact, that gives you a functor. So now I have obtained, I put it J for Jones. Sometimes I call it the Pythagorean functor, whatever of your taste of today. That will give you a functor from the representation of the Pythagorean algebra, because it's the same thing than the functors, to the representation of F. And to me, this is a unitary representation. And actually, if you, because everything is monoidal, is very nice, you remember Thomson's group T and V, they are made of F by adding permutation of leaves. Well, here you can just permute the direct summand, and you can lift this into representation of the other Thomson's group. So you get actually two new functors, two additional ones. So one choice of isometry from H to H plus H give you a representation of the three Thomson's group. Okay. And everything is compatible, everything restricts, just like you would expect. Now, perhaps I should tell you that you can also get a representation of the Cuntz algebra. Because actually that was the one in my title, right? So I should definitely talk about that. So what about the Cuntz algebra? I would say it's even more natural. You can see it as expanding this with Birgit Nekrashevich, but actually there's something even more easier to see. So you take now, you have fixed again AB in B of H with the isometric condition. Okay. And now you have constructed this H infinity with this inductive limit over trees of HT. Okay. And one way to see it is that this is really the set of decorated trees with vectors.
I mean Christmas trees.
Yeah, that's right. It's Christmas trees, basically. Yeah. And you have this equivalence relation, which is the equivalence when you embed HT in H of a bigger tree. Okay. And then you need to complete because you want the Hilbert space. All right. So what kind of very natural operation you have? Well, imagine you have something like that. That's a vector. Well, let's look at very natural operation. Well, first thing that you could choose to only remember the left-hand side or the right-hand side. Or you want to put that on a bigger tree on the left, let's say. So I'm just adding one caret below. And then the new guy gets 0. Or you just put it on the right. Okay. Well, I claim that here they are the generator of the Cuntz algebra, and they are adjoint. Alors, which one is which? I guess this one is going to be an isometry. I'm going to put S0 because with the first half of my Hilbert space, this is S1. This is S0 star to come back and S1 star. Okay. And you can check here, you get like a representation of O. Okay. Moreover, something interesting is that if you take, how does it work? I always get it wrong. Okay. You take S0 star and you you restrict to the copy of little h. This is your operator A you started with. As S1 star on the little h is B. Okay, so this representation really strongly encodes the representation you started with. Okay. And once again, you get the functor. Right. Okay, well, maybe that was a bit much, but I just would like to show you in diagrams how this works. Okay. So now I think I've been very slow. I have 25 minutes. I'm going to go back to the slides, give some statements and some explicit examples. Okay. So that's the plan. Maybe I'm going to go back to the big screen also for me. Oop. All right. I managed to do that. Okay. Sorry, just 1 second. Oh.
Oh.
Okay, that should be. Is that good?
Yeah.
Should be. Thank you. Okay, so this is basically what we have done here with constructionist Pythagorean algebra, and we've seen one-to-one correspondence within star representation, linear isometry, and monoidal functor of my forest category. Okay. So it's great. We get unitary representation of FTV. Actually, quite easy. Once you've seen it, it's easy to get it, but you know, it was great to have it. And also, everything is compatible with the Birget-Nekrashevich embedding. Okay, so everything works well. Yeah. In fact, so now I can answer also to a question before, which was like for this specific class of unitary representation, we don't get all of them. And in fact, it's interesting to note that the one you get, the representation of F you get, are exactly those that extend to the Cuntz algebra. Okay. So when you take a representation of F, you get in particular a representation of a subgroup of the unitary group of the Cuntz algebra, and it could extend or not. Well, those who extend are exactly the one I just showed you. Okay. All right. So now I have my 4 functors. Okay. And what we want to do is to construct, study, classify representation of FTVO using this easier C-star algebra, yeah, to deal with. The one that is basically Cuntz, but you're missing the relation that gives you isometries. Okay. So do we get all representation of FTVO? Well, in fact, you get all of them for the Cuntz algebra. How you prove that? Well, basically, you apply twice your functor, and you realize that the second time you apply it, nothing happens. So well, it shows you that your functor is essentially surjective, so you get all of them. But for FTV, you don't get all of them, as I just said. Are there properties that, you know, representation of P are preserved? Well, actually, yes, there are some. I don't know if I will get in details on that. I may go a bit quick on this. But there are 2 key properties that are conserved. And now arrive classifications, because that was the main thing I would like to study. So if you start with something irreducible, do you get something irreducible? Well, we're going to see sometime, but not always. Okay, so it's kind of shows that the subtlety of the question also. And can you classify them? Like if they are different at the beginning, are they different at the end? Well, again, sometimes it works, sometimes it does not. Now I'm going to explain a bit better the sometimes. Okay, so I may pass everything on diffuse and atomic. I just want to say that for this representation, the world is split into diffuse and atomic. And every representation is a direction of something diffuse one and something atomic. And if you look at the atomic, for the Thomson group, it's boring. Okay, they are all quasi-regular. So in fact, they are monomial. So they are like the induction of a one-dimensional representation. Okay. And if you know that, then it's easy to classify them. You can just use Michael-Shoda theory that is, so this I don't know when it is. I guess it's the 50s. But maybe I'm going too much in time. No, I think it's the 50s. And so you could create them and classify them without all this technology. Like this technology does not justify such stuff. One thing interesting is that many people look at atomic representation for the Cuntz algebra, Bratelli, Jorgensen, Bergman, Cuntz. I could cite probably a 10 article on this. But I don't think anybody realized that they were restricting to monomial representation of the Thomson's group. Because once you know that, then using classical work of Michael and Shoda, it's easy to classify them and it's easy to decide if they are reducible or not. So it's an interesting fact, actually, for the atomic. All right. Now, what about the other ones, the diffuse? Well, they are the total opposite of the atomic, okay? They are in mixing, where it means that they don't contain any induced representation of something finite dimensional. Right. So one key example that I really enjoy is just take the one-dimensional representation of the Pythagorean algebra. So what does that mean? It means that you need to take two complex numbers such that their modulus square is equal to 1. So here I just wrote down the real three-sphere. Any point of the real three-sphere give you a representation of P and therefore of F, T, V, and O, the three Thomson's group and the Cuntz algebra. So now what are these representations? Well, if I look at 1, 0, so perhaps the first example you want to look at, this will be reducible for P, but look, here it's split in two. There is a trivial and there is a quasi-regular. Well, actually, that's the only bad example. If A or B is equal to 0, and you look at the representation of F, that's the only time when something reducible don't give you something irreducible. The only time when you start with something finite dimensional and you don't get the nice correspondence. So now I say I don't want to have 0. Okay. Well, it did give you diffuse representation, and they're all pairwise non-equivalent. Okay.
Sorry, just a stupid question. Why do you denote the sphere by S3 of a subscript?
Well, actually, thank you for raising that. So I was watching a seminar of Jean-Pierre Serre, and he was saying he was a bit tired of seeing topologists putting indices on top when they don't mean product but dimension. So I know that most people put the 3 on top, but I have to follow Jean-Pierre Serre's advice. So that's why I put the 3 below.
Okay, so blame it on him. Okay.
Okay. No. Yeah.
But why C2 then?
What's that?
But why C2 then?
For L2, you mean? No.
Well, it's not a dimension. L2.
You're right that L2 is psychologically difficult to put the 2 below, but I've seen article. I wonder if Gilles Pizier does that for the LP. Maybe he puts the P below, actually. I've seen it sometime. Well, anyway. Yeah, convention really stick in the head. Yeah, it's hard to escape them. Yeah, one thing, if you take 1 over square root of 2, and this is very remarkable, you get the Koopman representation. Okay. And now you can twist it easily. You can just put one complex number of modulus 1, you divide by square root of 2, and you get a one parameter family that deforms the Koopman. And actually, this was discovered in a different manner by Gankarek. He saw it as an analog of principal series of representation of SL2. Okay. And if you take like these numbers, for example, you get like another family that was studied before by Oleson in a different ways in his PhD thesis. I think it was following an advice of Mono, actually. Maybe Mono and Musa. Wow. Okay, so that's the one-dimensional representation. And you can see that here we get explicit moduli space because it's parametrizing unitary classes of representation. So we could wonder what happened in dimension 2, 3, etc.
Yeah, where is the question?
Was that? Yeah.
Can you go back to the previous
Yeah,
slide?
the
for the
previous
question?
slide. And
Yeah.
I'm just wondering, some of these representations that you show that come from this construction in the examples, they would be clearly amenable in the sense of Becker. You know, I wonder if all of them are. I wonder if all of those that come from this construction would be amenable in the sense of Becker.
Well, it's it's a great question because I'm not too much familiar with that, but I was talking with Jacopo Bassi last week in Rome, and we were talking about the work of Jacopo is here, of Jolissin on the Koopman representation. Is exactly the question we came out from this discussion.
Koopman, and also I'm pretty sure that this quasi-regular representation, lambda f divided by f half, it should be amenable as well, but others I cannot see. Yeah,
I think remember is that Jolissin also look at f modulo fp. You're right, like a given So my guess is that probably they will all be amenable, or at least when you start with a finite dimensional.
Right.
Yeah, that's what I would think, but I have to admit I've never worked with Becker amenability, so but yeah, that would be a suspicion, yeah. Thank you. Yeah, so what about higher dimension? And here, I didn't say it, but if you want to classify representation, well, as I was saying before, for the Cuntz algebra and Thomson's group, everything is infinite dimensional or one dimensional. But if you take the Pythagorean algebra, you have all kinds of representation. You have all of them. And you can use representation of P to define a new dimension function for the Cuntz algebra or for representation of F. So take a representation, let's say, of the Cuntz algebra, and you look at all the pi such that they are sent to this representation. And you know that there is at least one. That's what I say before. And you just take the minimal of the dimension. And I gave you a well-defined dimension function for all all representation of the Cuntz algebra. Okay. And what I want to say, so maybe I'm gonna go a bit. I guess I still have a bit.
I have a question.
Yeah.
Could you go back one page? Yeah, about this parameterization of these representations. So these are simply representations. There are not isomorphic classes of them.
Yeah, so here they are just representation, but actually you can prove, well, let's say, let's remove the F case, but take T, V, and O. They are all pairwise non-isomorphic.
Oh, I see. So this is really a moduli space.
Exactly. Yeah.
Okay, thank you.
Yeah. You're welcome. Thanks for the question. And actually, if I go in higher dimension, the same is true. If I keep finite dimension. So maybe I'm going to go to the theorem. So here on the left, I'm going to take representation of P that have finite dimension. Okay. And then there is like, I don't want to be atomic. Actually, I could keep atomic, but whatever. But one thing important is that I will ask that there is no, what am I saying? Maybe I should do something a bit easier. Let's say that here I take the irreducible one. And they are finite dimensional. Well, they will be sent to irreducible representation on the right. And if they are pairwise non-isomorphic here, they will be pairwise non-isomorphic here. So this means now that if you find moduli space for the left, you have moduli space for the right. This works very well for T, V, and O. If you want to do it for Thomson's group F, you just need to discard the bad one. And the bad one are the one-dimensional atomic ones that I show you, the ones that give you, well, the only one you need to discard are those ones, basically. Okay. Possibly twisted by a phase. But for any higher dimension, providing that the dimension is finite, irreducible on the left give you irreducible on the right, and you can classify them pairwise. So, I mean, this was an amazing, we were extremely happy to find that. That was with Dilshan. That was really the culmination of, I mean, that was the third article on that. And this is something we did not expect at the beginning. Yeah. And so what does that give you in terms of moduli space? So here is what that gives you, just to be, you know, to arrive to really what I found the nicest.
Sorry, can you hear me?
Yeah.
Yeah,
I can hear you.
Could you come back one page?
Yeah, sure.
Could you explain this dimension P? Fine.
Oh, yeah. So you fix, let's say, yeah, one representation of the Cuntz algebra, let's say. And you know you can find at least one P, such that one pi, such that G of pi is isomorphic to it. So now the pi is a representation of P, the easier algebra. And you just take the minimal of all these dimensions.
So this is the same J. What was the functor?
Yeah, that was the functor that goes from representation of P to the representation
so left,
of the
so this functor and this notation dim dimension P dimension, they're related.
Yeah, they are built a bit from the functor. Yeah. If you want, if I go here, this representation with they are one-dimensional for P, and so the induced representation of the Cuntz algebra, we're going to say that the representation of the Cuntz algebra have Pythagorean dimension 1. So the dim P dimension equal to 1. Okay.
Yes, I understand it, but I'm asking about the dependence of the right-hand side of this functor on this functor itself. No,
you mean because here we're
you have this equivalence between representations of P.
Oh, here you
mean. Yes.
Yeah.
So J is also involved on the right-hand side. So this equivalence, in a sense, is not pure in the sense that you have two independent things. Right-hand side depends on this functor.
Well, yeah, you want to say that the representation you get on the right, they are built from representation of P that are finite dimensional. Yeah.
So this is more convoluted than.
Yeah.
It's not like you have one category, another category, and you have an equivalence simply. The second one, for instance, explains the first one. They are somehow related more.
Yeah. So the category on the right, if you want, is a full subcategory of all the representation category. You just took this subpiece, and what is remarkable is that you have bijection on the home spaces. That's what is remarkable. The whole
full faithful embedding it's a fully faithful embedding if you drop this condition of dp smaller than infinity.
I guess so. Yeah, I mean, all I want is that,
okay.
Yeah.
Okay, good.
Like we keep, yeah, we want bijection on home spaces.
So it's an
yeah.
it's an equivalence with the essential image of the functor.
Yeah, on something smaller, like you get like a.
Okay, thank you.
No, I'm going a bit fast, so it's a bit. Yeah, so what do we get? Like, so now I'm just going to restrict to iso classes of irreducible representation. Okay. So because I have my Pythagorean algebra, it's very easy to parameterize actually irreducible representation of P. Now I can just use my functor to move my moduli space to moduli space of F, T, V, and O. And so what do I get? Well, I can see that the space of irreducible representation of P of dimension, let's say D, is just a manifold of dimension 3D squared. One can just see that. If you look at all isometry from C power D to C power 2D that are irreducible in a certain sense, I'll give you a manifold. And then if you want to classify that, if you want to take classes, well, on the left-hand side, just need to act by conjugation by the unitary group. And since I act by conjugation, I may take like the projective unitary group. So I take PSUD. And I take the orbit space. And this gives me exactly iso classes of irreducible representation of FTVO. So that's how it works. Yeah. And so it also shows you that for any P dimension, okay, my new dimension function, there are many irreducible classes. So it's a meaningful dimension function because for any D, you get a manifold of this dimension. Okay, so you get like uncountably many isomorphism classes of irreducible representation of a given dimension. Okay. Do I want to say more about that? Well, maybe, well, the way, maybe I'm just going to write down a little bit just for the very end. Because that's the way I think about it. So let's take the spectrum of O. So this is like the isomorphism classes of irreps of O. And I just say that here I have a dimension function, so I may just write it as a disjoint union for D in N union infinity of the one of dimension D. Okay, so I can write that. Now, all the classical theory tell me that spec O is pathological. By general theory. But now I'm telling you that any of these guy, if I fix this guy.
Sorry, the topology you are using is a Jacobson topology?
Yeah, it's a pullback of the Jacobson topology when you go from the spectrum to the primitive ideals.
Okay.
And if you look at what it is, it's a coarse topology. Since my sister algebra is simple. We don't have much. So if I take a D different from 0, this is just a smooth manifold of dimension 2D squared plus 1. Okay. So basically, I gave an explicit bijection of this piece of the spectrum with a manifold of dimension 2D squared plus 1. So it's really like a moduli space in the usual sense. Yeah. Okay. And of course, it's a bijection. Nothing can be canonical when you talk about moduli. because you take a parametrization, just like you cannot say that there is a canonical base for vector spaces, right? But we get it, and they are quite natural from this point of view, because you get with a Python.
You have also this assumption of being diffuse, or not?
Alors, yeah, that's right. On the slide, there is diffuse. I put diffuse to have like everything works well for the Thompson's group F. But in fact, it works also for the atomic one. And actually, I'm glad you asked the question, because if you look at the atomic representation inside that, they're just, it's a subvariety of dimension 1.
So what is written on this slide is correct. You don't need any additional assumption for this statement to be true, yes?
Yeah. What I'm writing here for the Cuntz algebra is true. Yeah.
Okay, without any additional assumption on being diffuse.
Yeah, that's right. Yeah.
Okay.
And actually, this guy, you could see that the atomic forms a one-dimensional subvariety for HD. For HD finite. So it means that it's a finite union of circles.
So, somehow I don't understand what is happening here. On the left-hand side, you have a coarse topology. Yes, the coarsest possible topology, trivial topology. And on the right-hand side, you have some interesting structure and disjoint union. So how it is possible?
Oh, because I just took my set, I write it as disjoint union. I say, if you just take the general theory, the topology that will be given to you is a coarse one. But if you use the work that we've done, we get like this moduli space. We can say that these pieces, spec 0D, they are in bijection with a very nice geometrical object.
So you obtained some way of parameterizing those objects, and this parameterization somehow motivates the natural choice of topology on the right-hand side, yes?
Exactly, yeah.
Okay, I see.
So the whole work is that, this finding this parameterization. Yeah, exactly. Yeah. Okay. Well, I think I managed to be over time, so.
Yeah, 1 minute, 29 seconds, yes. Sorry, 2 minutes.
So thank you very much for the attention, and thank you also for the question. Yeah.
Muito obrigado. Any questions? Florita first. No? Everybody happy? Brazil is happy. Now, how about you Zoom folks? Adam, Tomek, Jacopo.
Yes, I would have a question.
Okay, if you would, go ahead.
Yeah, so what part of this theory could be extended to this how is it called, to this category of fractions of trees?
What part of
Because you were using this embedding of your is it all this story, is it all about properties of this group, or what part of this depends on this embedding into fraction category of trees? Yes.
Well, I mean, the thing is that if you take the category of trees, or category of forest, and it's true, I look at the fraction groupoid, and I say, well, inside I have my Thompson's group F as one of the isotropy group. But in fact, everything we do is really for Thompson's group F. But I would say F is almost as rich as the fraction groupoid, and I'll tell you why. Because the fraction groupoid is connected, so it means that every isotropy group are isomorphic. So it's kind of a bunch of copies of Thompson's group F
Yes.
that are linked to each other. So there's not much that you get from the group weight with respect to the group. Yeah.
Nice.
If you change to binary to n-ary, that would be different. And if you add like some permutation, that would be different. Yeah. But to be honest, I've been really working more like with the groups rather than the groupoid, although the whole technology is made for the groupoid. So one could also make statements there. Yeah. For example, there were some statements I proved for high group property for groups, and you could promote them to high group property of groupoids immediately. Yeah, because everything, the setup is made for that also. Yeah.
Is it possible to compute moduli spaces of functors into Hilbert spaces then?
Well, I mean, here, you know,
what real algebraic spaces you could obtain?
Yeah, they are in bijection. There is this nice one-to-one correspondence anyway with these monoidal functors and the representation of P of the Pythagorean algebra. So you could get moduli space. It would be just a different interpretation, I guess, of this parameter.
Yeah, but your spectrum OD, they were like let's say Grassmannian, something like this. But if you have representations of this fraction of F groupoid, then you will obtain some systems of very nice algebraic real varieties. So I'm trying to understand what kind of systems you could obtain.
I mean, you're saying, like, for example, if you don't look at Hilbert spaces, but you look more like linear representation, like in an algebraic context, or so you can do that actually. But something we did after is that you can redo the whole story with just the category of vector spaces, and you get the Thompson's group, but now the Cuntz algebra is out. Now it's the Leavitt algebra. And now what replaces P? So the picture will be that, like we had P, we had F, T, V, we had O, we had functor from this to Hilb. You could redo everything. When you go to Vec, O will be the Leavitt algebra. You still get the same group, but P will be even better, the free algebra. So here we are doing everything binary, will be just the free algebra in 2 letters. So every representation of the free algebra will give you a representation of the other guys. And here you'll get some algebraic variety.
Are these algebraic varieties complexifications of these algebraic varieties in the first classification?
Well, if you take well, no, they are different. They are because here for P, you had to deal with isometries, and that give you some manifold of dimension 3D square that after you reduce to TD square plus 1 for having the iso class. Here you get the free algebra, so there's no limitation. You just get 2 matrices of dimension D. So there is no limitation by the isometric condition. So they're kind of larger, if you want, in dimension. And if you take in over the complex numbers, they are the so-called Nakajima quiver varieties. It's exactly what you get. Yeah.
Okay. Thank you.
That's a nice story in the algebraic context. Yeah.
Okay.
Beh, Jacopo, prego.
So the Thompson group acts on the boundary of the tree. Do you know if the Koopman representations for quasi-invariant measures can be retrieved with this procedure?
So you're saying, yeah, so I take F that act on the boundary of the infinite binary tree.
Yes.
And then you'd like to take the Koopman of it.
With respect to quasi-invariant probability measures,
To a certain.
is there any possibility that these are obtained from this procedure?
Well, I would not know. Yeah, this I don't know.
Okay.
Yeah.
Okay. Thanks.
I think actually I was wondering. I think Medinet and Dudko, they look at these kind of things. I think they look at some kind of representation like that, not from this point of view. So maybe, but I don't know enough this kind of representation to tell you. Yeah.
Thanks.
So far, the only one we can really understand precisely, the representation we get for Thomson's group F will be some kind of. Okay, so L2, maybe I put the 2 here. Okay. To not contradict myself in the talk. We get representation like that. And P will be just a point of the Cantor space. So we get the quasi-regular, and that's the parabolic subgroup. Yeah, or the Koopman, as I was saying, yeah. Twisted if you want. But if you get the Koopman of L201, you will get, maybe we can get, it's kind of just changing the measure on the Cantor space, right? I guess. But I really don't know. So yeah. It would be nice to have a...
FP is amenable. Or not? FP is amenable. This the stabilizer of the point is known to be
but yeah. Since amenable in the Becker sense, yeah. So this really I don't know. I would really like to know. Yeah, that would be a good thing to investigate.
Thanks.
Yeah.
There is a question. What was the question?
About the Koopman.
About the Koopman? Yeah.
Yeah.
Oh, but the Koopman is well, you know, the one you will get from just choosing these two elements for the representation of P.
What was the question? Sorry.
Oh, of Jacopo? He was asking about if we can realize the Koopman representation of the action of F on the boundary of the tree or on the Cantor space with certain measure. Yeah. You take various measures on the Cantor space, you act on it with F, take the Koopman. Can it be given by this kind of Pythagorean representation? Yeah. Or do they share many common properties? Yeah. Well,
because this is related to something that Goldbrin was trying to understand. If the action on the boundary is amenable. So if one has something like this, then okay.
So I guess it will be, the question is equivalent also to know if they are Pythagorean. I mean, if this representation of F acting on the boundary extend to the Cuntz algebra. This I don't know. Yeah, but that's the same question. Yeah.
I'm not sure whether my question will make sense, but nevertheless, let me try. So coming back to this topology of the spectrum, so is there any hope to generalize this theory in order to obtain some general procedure to define a topology on a spectrum which would be more well-behaved, you see?
I mean, so everything works here because we kind of have a nice pair of sister algebra that magically work, like P and O. And in a way that O is a quotient of P. So you could extend that to other cases, such as Kuntz-Krieger algebra, or other things like that. But in general, I just don't know. Like it's really specific. Like you need to have like certain universal sister algebra with specific presentation. the tree structure permits you to remove certain relation. So in some sense, for me, P is a universal C-star algebra generated by this relation. You could kind of make sense of that. While O is a universal C-star algebra generated by, having two relations. If you think more in terms of representation theory. So you could certainly find other pairs of examples where things work well. But to me, it would be too much to go. Like, I don't think you could for everything. Yeah. So my answer is, I don't know. I know for specific other example, you can do something similar, but I don't know to what extent you could do that. Yeah.
For example, for non-commutative tori.
Well, non-commutative tori is actually it's a quotient of P. Yeah, of the Pythagorean algebra. So I wonder what you could do. So it means that any representation of the non-commutative tori actually go here.
Yeah.
Is here. Yeah.
Yeah.
So I guess the technology I'm giving you would maybe help you to classify them. Yeah, so actually it's an C-star algebra that is, fairly nice for this setup. Yeah. Yeah, could be possible that there's something to do here for the spectrum of the non-commutative tori. Absolutely. Or Cohn-Landis sphere. They enter with this framework. Yeah. The one of Giovanni Landi and Cohn. Yeah.
Can I ask one? Yeah.
Very
I
nice.
want to ask one last question, if I may.
Mhm.
So has anybody ever looked at this, if this representation that I'm going to describe fits into this scheme? So actually, Zhisi Sergeyev have proved that you can conjugate Thomson's group. It becomes a group of diffeomorphism, right, of the interval.
Oh, that's right. Yeah.
And then you can embed it into the diffeomorphism group, and you can move the classical Wiener measure on this group, right? Just it was done by various people like Chapulis and Paul Maliavin that have done this. And then you get, with the Wiener measure, you get, it's quasi-invariant, and you get a representation. So I just wondered if anybody looked at this representation from this viewpoint, does it fit into any scheme or? From this quasi-invariant measure on the group of diffeomorphisms, you can restrict it on the Thomson group.
I don't think it has been looked at. Yeah, because we look at many representation of the Cuntz algebra, and so we will restrict here. And I've not seen this one, at all. But actually, I'm curious about how you do that, because I'm aware you can embed F in diff S1, but I'm not aware about what you do after. So I'll be curious to look at that. Yeah,
it's a canonical way to transfer the classical Wiener measure from continuous functions onto the group of diffeomorphisms. It's not very difficult, and it becomes quasi-invariant, so it gives rise to representations of the diffeomorphism.
Okay, so you just like the embedding, then you pull back this Wiener measure, and you look what you get.
Is sort of using logarithm and non-linear method between the two.
Okay. Yeah, I've not encountered on them, but I look at many representation, but I've not seen that. Yeah. Okay. It could be interesting to see how much they share. Like if you feel that they have similar properties, they could be. Yeah. It's also interesting to see what is at the edge, because here we see that these representations are exactly those that extend to the Cuntz algebra, but with this different point of view that kind of give you a bit more analytical properties of them. And so what could be something that looks very similar, but actually is not. Yeah, I'd be curious to find. Yeah. Okay, so thank you for the candidates. Yeah.
Okay, let me wind it up by asking you some very elementary questions, if I may. So for starters, what is the kernel of this surjection here? What is the kernel?
So what did you just say?
What is the kernel of this surjection here? I'm writing on your screen.
Oh. Yeah, okay. So let me write down again the presentation. Get your pink. That's following me. So I got, so P, maybe it's better if I write it with a notation. If I will write with the notation of Cuntz, it will be a bit strange. I will write it like that. Oh, I guess, what am I doing? Yeah, because well, I write the map with a classical notation to not write something wrong.
Yes. Mm-hmm.
And here it's S0, S1, and then SI, SJ is delta LJ, right?
Mm-hmm.
Okay, so this is the map.
Exactly. Yes, of course.
Yeah.
Yeah.
It's the map. So we remove the second isometric condition. We only have one. Yeah.
Mm-hmm.
Yeah. So.
Yeah, but what's the kernel?
I guess it's
in terms
Ideal
is what
generator.
compact operators. Yeah, this I know, but I was wondering if you can give me a concrete answer how the kernel is compact operators or compact plus compact.
Yeah, I mean, yeah, I don't know how much more I can say from. That's what it is. Yeah, I just need to force them to be isometries. Yeah.
Yeah, sure. But the resulting ideal is what? Am I right guessing that these are compact operators, or am I wrong?
Well, actually, I don't know. I never thought about that. Yeah.
Okay. Okay.
But I think that
I like that you start the question by saying very elementary. I'm like, well, I don't know.
Sorry.
But I think that there would be maybe problem with compactness since those are what partial isometries. So usually something in the spirit of being close to projection after all, infinite dimensional. So
Well, I mean, when you force isometry to being unitary, the kernel is compact, right? So somehow
that's your
you're just flipping the star and requiring one more relation. So that's why I guess compact. But okay, the second, you had this very nice picture comparing P and O, I mean, Cuntz and Pythagorean sister algebra, saying that here you have one relation, here you have two relations. Is my, okay, actually this is, my question's answered already on this slide. So you are kind of removing one of the Cuntz-Krieger relations and keeping the other one. But this is funny because when you do Teplitz sister algebras or Kohn path algebras, if you want, when I say Kohn, I mean COHM, then you are typically what you are doing, you are ignoring the second Cuntz-Krieger relation and you keep the first one. And here you kind of do the opposite. You are forgetting the first Cuntz-Krieger relation and keeping the second one. That's kind of interesting. This kind of reversal, I've never seen it before. Okay.
But it's also, it will be the same when you do quiver algebra versus Leavitt path algebra.
Okay.
You kind of, I mean, here it's even stronger because you remove generators, but it's kind of the same spirit, yeah.
And what is quiver algebra? I've never.
I mean, the quiver algebra. Well, if I take the usual one,
yeah,
that would be the free algebra on the left for the Leavitt. So if you take like this thing, you'll get like this. Usually they are written like that. And on the left, you just get E1, E2 with like no relation.
Okay.
So you don't get like the other side, yeah.
Okay. So this looks like the path algebra of this problem.
Exactly. Sorry. Yeah, the quiver algebra is really like the path groupoid or whatever you want to, or path algebra, how we take it. Yeah. Yeah. Exactly. You can compose the edges with each other. Yeah.
And I was also wondering, you focused your talk on O2, but inside O2 you have all other Cuntz algebras. So can you conclude anything about the other Cuntz algebras just by restrictions, or is it complete nonsense?
Well, I mean, you can. Me, I would more like take like everything NRE. Just we do everything with NRE forest.
Okay, so you generalize the procedure. Okay.
Yeah, I would do that. It works fairly well, but it's very interesting actually to play with embedding and things like that, endomorphism, and to reinterpret here. And it gives you very nice maps. Actually, many maps are very mysterious still at this level. Some of them play well with the moduli space, some other I don't know. But yeah, actually, it's very interesting to look at that. Yeah.
Okay. And the final question, Tomek, and then we end.
No. My question was already answered. This was my question. Yes.
Okay, perfect.
How to see this embedding in terms of this forest?
Yeah. Okay, so in this case, let us obrigado our speaker again. Thank you so much, Arnaud. Merci beaucoup.
Je vous en prie. Merci à vous. Well, thank you for all the great questions. It's really a pleasure to have a nice feedback like that and get like actually, good direction.
This is what the seminar is for. Thank you so much. I stopped recording.